Applications of Sinusoidal Functions, Part 1, the Spring 2020 version. So for the functions review, y equals a sine b bracket x minus c plus d, or the cosine version. So the median value is d. The median, or the midline, I'm just going to adjust that line, is d. The period, or the length of one cycle, so the period is 2 pi divided by b. The range, so if this is the middle, and this is the variance from the middle, then we will go from d minus a to d plus a. And we'll set all y such that. So from the middle minus the amplitude, that takes you to the bottom, and the middle plus, oops, yeah, that's okay. How can you find the maximum value? Well, the maximum value is d plus a, and how can you find the minimum value? The minimum value is d minus a. A function whose graph resembles a sine or cosine curve is called a sinusoidal function. Many periodic phenomena can be represented. A few examples are the height of a chair on a Ferris wheel. So think of a Ferris wheel, it's going up and down. Time of sunrise as a function of the day of the year. So the days are getting longer now, the sun is rising earlier. And the depth of the ocean due to changing tides as a function of time. The x and y axis will represent different units, but our knowledge of transformations on y equals sine x or y equals cos x help us to interpret the data. Unless stated otherwise, all application questions will be done in radian mode on your calculator. 5 seconds, 5 meters will have the same value as if it were 5 radians. And actually, that's where B comes in. What B is doing for us in an application question is it's changing from whatever the x-axis units are, or theta or t if it's the x-axis, the theta, the t-axis, whatever, is changing from those units into radians. So it's converting into radians. All right, let's take a look at example 1. Pendulum swings back and forth. The equation that represents the horizontal distance in centimeters from the 0 position. Got to see where I'm at here. So the 0 position and the horizontal, nice horizontal line, the horizontal distance from the 0 position at t seconds is h of t is 5.6 sine pi over t. In a question like this, we assume the pendulum keeps swinging as if there was no gravity or friction slowing it down. Determine the maximum horizontal distance of the pendulum bob from the 0 position. So if we look at the equation, a sine b x plus c plus d, then we can see that a, in this equation, a is 5.6, and that b is pi, that there is no c, and there is no d. So from the 0 position, we're going to move 5.6 to the left, 5.6 to the right. So the maximum horizontal distance. Horizontal distance is 5.6 centimeters. The time, well, the period is 2 pi divided by b. b is pi, so 2 pi divided by pi is 2, and that's in seconds. So 2 seconds. Sketch 3 cycles of the graph and label the axes. 1 cycle of y equals sine x is drawn on the same grid for you to compare the graph's equations from a transformation point of view. Okay, so this is sine x. Now we know that A is 5.6. That's probably a bit higher. 5.6. We will go as low as negative 5.6. Our midline, this is going to be our midline, so we'll start at 0, 0. Our period is 2 seconds, so we'll be back to the midline every 2 seconds. And a sinusoidal curve is split into 4 parts. So if we split 2 seconds into 4 parts, each of those will be a half of a second. So in a half a second, you'll reach the maximum. At the next half second, or 1 second total, you'll be back at the midline. And the next half second, you'll be down at the minimum. Then back to the midline, half a second later, to the max, to the mid, to the min, to the mid. 4.5 seconds will be at the max, back to the midline, and so on. And so now we can sketch this out. We can see how well we can sketch this out using a tablet. I was going to say it's not bad, but it's getting worse. Alright, it's not, well, other than this bit here, it's not horrible. It started out okay. Determine the horizontal distance of the pendulum bob 1.3 seconds into the swing. Okay, so we have the equation. H of t is 5.6 pi t. H of t is 5.6 sine pi t. So 1.3 seconds in, 5.6 sine pi 1.3. Let me just grab my calculator. Make sure that it is in radian mode. And I suppose I could be typing on this calculator. Eh? Let's pull up this calculator. Let's close that window. Okay. Let's see if we can drag this over to the right. Almost. Okay, so let's clear this out. Let's check the mode. So we are in radians. So clear out of that, and we're going to go 5.6 sine. I'm just going to go 1.3 pi. This is easier than using it on the board. 5.6 sine 1.3 pi gives us negative 4.5. So the horizontal distance will be 4.5 centimeters to the left. Did they give rounding? I don't know. So negative 4.53 centimeters. Let's put that way. It doesn't say. Hundredth is good to me. Example 2. If all the times were recorded using Mountain Standard Time, an equation that represents the sunrise times in Calgary over a year is approximated by this, where t is the time in hours after midnight and n is the day number starting with January 1st. Okay. So, for example, January 9th, n will be 9, the 9th day, February 1st, n would be 32, and, if it were this year, then we would have, but we're not, we're going with a generic non-leap year. So, one cycle of sunrise times, really what this is asking is what's the period? So the period is 2 pi divided by 0.0172. Calculator, which is now in the way. 2 pi divided by 0.0172 and gasp, 365 days. Well, that sort of makes a lot of sense, right? So 300 and excuse me, 65 days. Write the earliest sunrise time of the year as it would appear on a digital clock. So the earliest is the minimum. The min, I was just going to write min, but is D minus A, which is 6.48 minus 2.17, which is, I'm going to need this anyways, and let's clear this out, 6.48 minus 7 is 4.31 hours. Now that's decimal hours, 4.31. And a digital clock shows hours and minutes. So this is a third of an hour. So here's what we're going to do. We'll subtract off the 4. So we've got 0.31. So we know that digital clock, it'll be 4. So what are we doing? We've got 4.31 minus 4 gives us 0.31 hours. And so what we'll do is multiply this by 60 to turn it into minutes, and it'll be 18.6, but a digital clock won't round time, so it won't go to 19 until it is 19. So if it also showed seconds, then what we would do is subtract off the 18 minutes and multiply by 60 to get seconds, and it would be 36 seconds. Okay, now we're only interested in this. 4:18 a.m., earliest sunrise. Determine the day of the year which the sun rises earliest. So for the day of the year for the sun to rise the earliest at that 4:31, basically this is going to have to be -1, right? But we can just do this. So if I put the 4.31 is equal to 2.17 sine 0.0172. Sorry, just every time I run near the edge of the tablet, plus 6.48. So this will be negative 2.17 is 2.17 sine 0.0172 and plus 106. Negative 1 equals sine 0.0172 and plus 106. Excuse me. So when is sine -1? So, oops, let's think about that. Right, that's 3 pi over 2. So 0.0172 times n plus 106 is going to have to be 3 pi divided by 2. Calculator. So I'm going to take 3 pi divided by 2. And we'll divide that by 0.0172. So that gives us n plus 106 is 270. Let's call it 274. So then minus 106 is 168. So day 168 So here we go. June 1st is day 152. So we're talking June 17th, well, 16 days later. Yeah, but about June 17th. And what happens in June? Well, that's pretty close to the first day of summer. So the sun is going to, excuse me, rise its earliest on around the first day of summer. From January 1st to December 31st, graphically determine how many days have a sunrise time before 6 a.m. Okay, so I'm going to need to see the equation. Put that over there. So we're going to go to y equals. We're going to put in the equation 2.17 sine 0.0172 x plus 106 plus 6.48. 6.48. Dang, I had a minus plus. Hang on. Just notice this. That would mess things up. Let's get rid of that. All right, let's set an appropriate window. So we know over the course of a year, so 0 to 365. We know the minimum time was 438, and the maximum is going to be around 8. So you know what? I'm just going to go X scale. Let's go 30. So each tick will be almost a month. Excuse me. I'm just going to go 0 to 10 here. And let's graph that. See if we've got what looks like a reasonable graph. So there's our minimum sunrise, right? It's about halfway through the year. So graph looks reasonable. And now let's, oops, let's scribble. Let's scroll down and say, graph determine how many days have a sunrise time before 6 a.m. Which means we're going to want 6 a.m. on here. 6. And graph. So for graphical, I'm going to write 2.17 sine 0.0172 plus 6.48. Sorry, mumbling. Y2 is equal to 6. We need to show our window, so 0 to 365 by 30. And our y values are, what I go 0 to 10 by 1. And we will show a sketch of the graph. So let's do that down here. And so that's y2, which is 6. That's y1, which is that. And what we now need to do is find the intersections, right? So we need to find out which day is this and which day is this. So we're going to do a second calc intersect. Second calc intersect. And so I'm going to move. This is so much easier than the whiteboard. Oops. 1, 2, 3. So 89.6. And second calc intersect. I actually could have just gone along the red line. It would have been faster, but what does time mean now anyways? 1, 2, 3. 246.3. So I would say it's day 246 minus day 90. So how many days? Quit out of that. 146 minus 90, I think it's 156. 156 days. So, graphical determination requires you to show what is your y1, what is your y2. Here's my scale. Here's a sketch of my window. This is what I'm doing. Right? These are what I'm doing it before. Just ran off the tablet. These are what I'm doing. There's my numbers. There's my answer. Describe the significance of the parameters. The parameter d in this situation. So d is the midline, but in this case it's the median, right? And what that says is that half the time the sun rises, if we stayed on Mountain Standard Time, half the time the sun rises before 6.48. So 6.48 is 0.48 is almost 0.5. That's really close to 6:30 a.m., just a smidge in front. So half the year. So 6.48 is the median time of sunrise. Half the year the sun rises. I just don't have an easy eraser anymore. The sun rises before. Alright, what time is that actually? So what we really just need is the 0.48. 0.48 times 6D. Enter 28.8. So we'll call it 6:29 before 6:20. Oh, there. Let's get exact. And half the time. And half the year. The other half the year. So the before, and when does it hit that? So here, like 90 days, right? 90 days is like around the end of March. So, oh wait, that was 6. Yeah, so around the end of March, right? Because the median time, the 6.48, it's going to reach that at spring. 6.48 is actually going to be sitting up here. And this would be spring. And this would be fall. So 6 a.m., which is the time we're interested in, is 90 days in. So that's around the end of March. And then fall would be September. And this is 246, whenever that is. And half the year. Half the year. Sun rises ran off the tablet after 6:28:48. Next. The piston in an engine moves up and down in the cylinder. You could run off to YouTube and go look something like this happening. The height h in centimeters of the piston at a given time t in seconds is given by the formula. H of t is 20 sine blah plus 20. Determine the maximum and minimum height. So in this case, both A and D are 20. So max is D plus A is 20 plus 20 is 40 centimeters. And the min is D minus A is 20 minus 20 is 0 centimeters. So this would be in the cylinder. So at the minimum, it's at the bottom of the cylinder at 0, and at the maximum, it's at the top of the cylinder. Okay, so period is 2 pi. Ooh, nice pi. 2 pi over b. So the b is pi divided by 0.025. Pi divided by 0.025. So that's 2, or, I mean, if you want, we could keep that times times 0.025. 25. over pi. So the pi's cancel. We've got two of these, which would be 0.05 seconds. So the period is 5/100ths of a second, which actually for piston is probably a pretty slow moving piston. And what we got here, YouTube, watch this video. All right, hang on, I'm going to pause this. Let's see if I can run off to YouTube and find this. Okay, here we go. Here's the video. Bay of Fundy. NovaScotiaWebcams.com. So you can see the tide height, 27, 29. These are the largest tides in the world, by the way. And now the tide's going out. So it seems to have peaked around 50 feet. That's a lot of water moving in and out. Tide goes in, tide goes out. All right, hang on, pause. And we're back. So example 4. So you have this on your sheet. You can read all of this as well. So I'm not going to spend a lot of time. You can always pause and read. But basically this data was collected, and in a graphing calculator, we can run a regression. That's what the video that this video is replacing did. And so we're not responsible in 30-1 for running regressions, but you basically enter this data into your calculator and you ask it to calculate a sinusoidal equation. And this is what we got. And I'm on the pointer. So I'm just going to switch back to the pen. So y represents the height of the tide, x represents the time in hours after midnight. And again, not part of the course, but analyzing this is. So enter this regression equation in your calculator. All right. So clear, let's go to y equals, and we'll clear everything out that's in there. So 7.21, 7.21, so 4, bracket x plus 0.16, bracket, one more bracket to close that off, plus 6.58. So we should already know what all of these things are, and I don't know if I'm giving anything away, but well, we won't. So state the period. So the period is 2 pi divided by b, which is 2 pi divided by 0.54. So 2 pi. Now, because order of operations is going to go in my favor, I don't need to put brackets around, but if I was dividing by, these two terms, I would definitely need brackets around there. So, that is 11.6 hours. Okay. Now, if you knew anything about tides, which if you live in Calgary, you don't, the period of tides is around 12 hours, so. State the high tide height. Hang on, I'm just going to go back to the... No, that's not going to show. So 6.58. So the max is D plus A. And remember, it just says state, but it doesn't hurt to show where things came from. So 6.58 plus 17 point... Sorry. erase that. Plus 7.21, so we got a 9 and a 7 and a 13. So 13.79 meters. State to the nearest tenth the height of the tide at 4:30. Need to change that into hours, so we need decimal hours out of that. Well, that's going to be 4.5, right? 30 minutes. Okay. So, state the tide of the height. The tide of the height. State the height of the tide. Let's go set our window. So we know that the period is 12. So if you're ever doing anything with your calculator and sinusoidal, make sure, pay attention to the B value, right? Like pay attention to A, B, and D, because they're going to tell you how to set your window. So let's go by 1 hour. And we know we go, I just like 0 for some reason, although it's, actually, it's, not a sec. Will the tide height go negative? Yeah, actually it will go a little negative, won't it? So the minimum is going to be 6.5 minus 7 and change. And we can see here in the table. So I am going to adjust my window accordingly. So Y min. So let's go -2. And we figured let's go to 15. Yeah, we could do that by ones. Let's graph it. We want the height of the tide at 4, so that's 4.5 hours. So second calc, number 1 is value, or just hit enter, give it a time, 4.5, don't put in 4.3. And we have 10.8 meters to the nearest tenth. Okay, now height is in meters, right? So the y-axis in this case, right? This is a height in meters, height, and this is time in hours. A boat was docked at this particular location. All right, hang on, I'm gonna run off, get the video of the boat. Okay, so a boat was docked at this particular location at midnight because the captain was getting so much needed sleep. The boat requires a depth of at least 4 meters of water. Graphically determine the time as written on his digit watch. His digit watch named Al. Al the digit watch. Which captain must leave the location while maximizing his sleep time. Oh, I think we're using the same equation. So, graphically determine. Y1 equals the equation which is on the previous page. Oh wait, I can pull it out of the calculator. 7.21 sine. Oops. 7.21 sine 0.54 x plus 0.16 plus 6.58. It's not a pointer. Okay, now let's get back. Don't mind me, just mumbling. So y2 will equal 4. Our x, so we do 0 to 12 by 1. Our y, negative 2 to 15 by 1s. And our graph looks something like this. And we have to go to y2, which is 4. Hit graph. So we need that 4 meters of water. So 4. So this is what we're interested in. Second calc intersect. Second calc intersect. Real close. 1, 2, 3. 6.335. So interestingly, that value is stored in x, right? So the time is 6. Okay, so let's get out of here. Second quit. Let's clear that. Let's bring in the x. So there's x. Okay, minus 6. And then times 60, because that's decimal time, right? So 620. So he would be advised to leave it 619. Actually, probably at least 4 meters. Yeah. So if he's staying until it's going to drop to 4 meters, then he probably wants to leave a little bit earlier than that, just to allow himself some time. Would be the wise thing to do. During the approximate number of hours round its nearest 100 that a person could stand on the ocean floor. So the water level is 0 meters. Well, 0 or below, right? So let's go back here, and we'll just make this red. So what we're interested in this time is here to here. So I'm going to pull up the calculator. We'll go to y equals. We will set this to 0. Graph. So it's going to be in this little area here. Now, one reason I like doing that as compared to going second calc 0 is because I could just do an intersect now, and intersects are easier than zeros. So second calc intersect. Because in an intersect, you just move to the point, and then you hit enter 3 times. So we have 7.79. Let's say, and second calc intersect 1, 2, 3, 9.35, 9.35 minus 7.79. So 1.56 hours. And remember, that's decimal hours. What did it say? Rounded to the nearest 100. So 1.56 hours. And we're done. All right. So this will be up on Schoology, and enjoy.